Good afternoon. On behalf of the Institute Colloquium Committee, I welcome you all to today's Institute lecture, Climate Change from Equator to the Poles by Professor Matt Collins. It is my honor to introduce Professor Matt Collins, who is a distinguished scientist in the area of climate science and also today's esteemed speaker. Professor Collins is the head of Department of Mathematics and Statistics and also holds the Joint Mate Office Chair Professor in Climate Change in the Faculty of Environment Science and Economy, University of Exeter. He has served twice the IPCC Intergovernmental Panel on Climate Change as the coordinating lead author, contributing to the 5th assessment report, which is known as AR5, and also special report on ocean and cryosphere. He has led several UK-funded projects, major projects, including emergence of climate hazards and robust spatial projections of real-world climate change and so on. He was the former editor of Journal of Climate and also presently the editor-in-chief of Frontiers in Climate. He has published more than 150 journal publications with more than 81,000 citations. Additionally, he is also the member of Cliver's Scientific Steering Group and also past co-chair of the Climate Dynamics Panel. So before we begin, I request all of you to kindly put your mobile on silent mode. And during the talk, it's preferred that if you don't ask questions or don't interrupt, at the end of the talk, there will be a detailed question-answer session and discussion where you can discuss with the speaker. Thank you everyone for joining. Now I welcome Professor Matt Collins to deliver the Institute lecture.
Thank you very much. Is this working? Yeah, I think so. So thank you, Subhamal, for the warm introduction, and thanks very much also for the invite to have what has been a very tiring 2 days of meetings discussing lots of things about water resources in India for the last 2 days. So yes, I'm Matt Collins from the University of Exeter. Exeter is a small city in the southwest of the UK, maybe about 3 hours from London. But it has a large concentration of climate science. So we have many people at the university doing climate science, but also in the same city, the UK Met Office and the Hadley Centre, who have several hundred scientists, working on modelling and observations and publishing many papers, etc., etc. So it's a good place to come and visit if you're into climate. It also has quite a nice climate, although not as nice as here. Okay, so what is this paper, or what am I going to talk about? So, what I thought I would talk about is try to do some kind of basics of climate change for those people who are not researching it themselves, but also to do some a bit more kind of technical or a bit more cutting edge kind of science. So what happened was that we had a couple of big projects in the UK. So these are nationally funded projects involving many scientists from the University of Exeter, from the Met Office, and other universities like Reading and Oxford and places. And what we did was to write a kind of paper. We wrote a synthesis paper at the end of this project, which drew together some of the main findings. So I'm going to talk about some of those main findings. Not really in very much detail, but it hopefully gives you some flavour of the sorts of work that we're doing in the UK on climate change. So this paper is published in a journal called Frontiers in Science. It's a relatively new journal. The idea is to bring together many authors to write these kind of big synthesis type papers. I'm sure this QR code won't work at this resolution, but you can Google the paper and read the conclusions. So, by the way, there are some animations in this PowerPoint, which is the reason behind this is someone helped me to do these PowerPoint slides. It's not something I know how to do myself. So if it looks a bit flash, it's because the Frontiers people did a lot of that. But you get, for this paper, paper is called Emerging Signals of Climate Change from the Equator to the Poles, New Insights into a Warming World. You get the main scientific content, but also there's some summary material. There's something called Frontiers for Young Minds article where we try and write something for children. So yeah, that's the main. This is the animation part. Ooh, yeah, and then there's also some commentary pieces by Dave Frame, Swadin Behera, and Shangping Ji. So they've written something of their own views on this particular subject. So you can. There's a package of papers around this. Okay, that's the advert over and done with for Frontiers. Now I can get on to talk a little bit about the science, but first I want to talk, for those who are not familiar with what we do with climate change, climate modeling, is to explain a bit about how this works. What do we do to study climate change? Well, we have obviously observations from all different kind of climate variables, temperature, rainfall, ocean temperatures, et cetera, but we also have these climate models, and the way these work is they're global climate models. You take the equations, the Navier-Stokes equations, which represent the fluid flow of the ocean and the atmosphere, and you put it on a grid, a horizontal grid and a vertical grid, and you solve those equations by time stepping forward. The reason the solving is done on a computer because it's not possible to solve the equations analytically. They're too complicated and they don't have simple analytic solutions. So we use big supercomputers. There are lots of these grid boxes all over the world. It requires a lot of computation. There's a lot of data output. But it's still not enough to solve the equations of the large-scale fluid flow of the atmosphere and ocean. We need also to represent what are known as subgrid scale physical processes. So these are processes associated with clouds, which are at a scale which is very much smaller than the grid box of the model. So there are clouds, rainfall, there are land surface processes, snow, vegetation. We have to model the transfer of momentum, heat, and water between the atmosphere and the ocean and the land surface. We have to parameterize the solar radiation and the terrestrial radiation and fluxes at the surface, et cetera, et cetera, et cetera. So these have become very complex models. The current version of the Met Office climate model is kind of around about 1 million lines of code written in an ancient programming language called Fortran. That was probably most of it's in Fortran 90, so the 90 is 1990, so you can tell how old it is. But it turns out still to be a really useful language for doing these numerical models. So we take these 1 million lines of code and we run the model forward in time, and we think about how the climate might change. And most of the work that I do and my group do is to actually try and understand what the model is giving us, because it's not known a priori what the model will show. There are some basic physics of climate change, like the Earth will be warming, but the way that the rainfall patterns shift around, et cetera, is not something you can get from a simple theory. Here's some example of some output from a whole collection of climate models. So this is the global mean surface temperature. So this is the temperature averaged usually at about 2 meters height above the Earth. So it's a surface air temperature. You can measure that with thermometers and with satellites, and you can get a good record going back. You can reconstruct going back in time to about 1850, believe it or not. This is the white line here. So what we see in the white line is an increasing global mean temperature. This is global warming, climate change. And then in the dashed curve, the gray lines are individual model simulations. So they, broadly speaking, capture the global mean trend, and then they project a further warming into the future. But different models kind of give different results. And this is one of the main kind of headaches about climate change is you cannot just run the model and look at the output and believe it straight away. You have to interrogate it and decide, whether you think the physics is right, whether you think it's statistically consistent, et cetera, et cetera. There's actually two curves on here. One is the red curve is the average of all the different models. And what you see is actually that's warming at a rate which is slightly higher than the observations. So what my colleagues have done in this study is to adjust, do some adjustment factor on the global mean temperature to bring the average of the models more in line with the observations. And there's a statistical model behind doing that. And the reason you might be interested in doing that is because it might make a difference. For example, this plot here shows the probability of crossing 1.5 or 2 degrees. No, it's the probability of the temperature, global mean temperature being greater than 2 degrees. So the red curve suggests that will happen maybe around 2050. But the blue curve, the adjusted curve, this pointer. Oh, yes. Let's start over here. The blue curve here, which is the adjusted one, which is warming at a lower rate, suggests that is that time of emergence, if you like, of the 2-degree warming is much later, or a few decades later. So this is, again, something that we might have to do with climate models. We don't just take the output at face value. We may have to do some adjustment, or we may have to just simply live with the fact that there's some uncertainty in the projections. And the uncertainty generally gets bigger as we get to more local scales, and I'll show some results at local scales. The point here is also that this curve is a balance between the warming effect of greenhouse gases and the cooling effect of aerosol particles, which are from pollution from diesel engines and power stations, coal-fired power stations, etc. And that balance may change in the future as we all drive cleaner vehicles and generate our electricity in more renewable ways. Then the aerosol particles are expected to go down, but there may still be a rise in the greenhouse gases. Okay, one aside really on the future. So we're looking at climate change into the future. We don't know what the future levels of greenhouse gases will be because that depends on lots of things about economics and society and adoption of green technologies, et cetera, global population. So usually we use these scenarios. I won't go through all this detail, but there are various scenarios for the future. There are scenarios in which there are a green world in which we have a lot of renewable energy, maybe not such big population growth, et cetera, and over here on this side is the very high scenarios where we essentially keep burning greenhouse gases until we run out. Just to say that you may see these things like SSP 245 or SSP 585. They're shared socioeconomic pathways. We are fond, as climate scientists, of looking at this very high scenario. That's not really because we believe it. It's because it gives us a good signal to noise from the model to understand the physics of climate change. So if you see papers which are using this SSP 585, it's almost the worst case scenario, but it's useful for us as climate scientists to get a good signal. And one other aside, just before I talk more about the regional patterns of climate change is this. You may have heard of the term net zero. So net zero means that we essentially stop emitting greenhouse gases at some point. It may be that we're still emitting some, but we can scrub those out of the atmosphere in some way, with some technology still to be developed probably. But I think a lot of people are under the impression that net zero means that we return back to the climate that we had before global warming, so the 1850 climate. That is not the case. These are climate model experiments in which we followed one of these very high scenarios. In fact, it was SSP 370, and so it's not the highest. And then we branched off these are global mean temperatures, branched off some simulations fixing the concentrations of greenhouse gases. So this is essentially saying, okay, no more greenhouse gas emissions, but we have to live still with the consequences of the greenhouse gases that we've historically put into the atmosphere. And you can see here in this case, there's still some kind of global warming happening after these concentrations are fixed, because there's inertia in the system coming from the ocean and maybe other factors. So net zero does not mean no global warming. Net zero means, less global warming than we might get if we continue to emit greenhouse gases. These are, this is a technical point, but these are concentration-driven runs. You can do this with a model which has a representation of the carbon cycle and essentially zero out the emissions. And in fact, eventually these curves do stabilize because there are aspects of the global carbon cycle which means that eventually the greenhouse gases that we pumped into the atmosphere will be absorbed by the biosphere. But that takes many hundreds of years, if not thousands. In the interim period, for the next few centuries, we're probably stuck with the global warming that we have, unless we can get to net negative emissions, which is another talk entirely. Okay, let me just check. Okay, right. So now I want to move on to talk about the main thing that we wrote about in the Frontiers in Science paper, which is regional changes. So this is not a comprehensive talk about all regional climate change. You have to go to something like the IPCC to find that. But it's 5 different areas, or maybe 6, where we've got some specific new results to show from the work that we did in these projects in the UK. Okay, maybe I don't need to explain what a monsoon is, but I'll do a brief explanation. Probably every Indian climate scientist has a paper about the monsoon, right? At least one paper about the monsoon. It's good, it's obviously important. So what monsoons are, generally, well, historically they were described as a sort of change in the wind, a shift in the wind direction. But they've come to mean, if you're looking up in the dictionary, which I did earlier, it's come to mean, a seasonal rainfall pattern, which is often quite predictable. It comes every year, but obviously there are, variations that happen within each year, and there are various monsoons. This is kind of like a representation of the global, sometimes called the global monsoon. So we have the famous South Asian monsoon, of course. There's a monsoon in East Asia, Australia, West Africa, and maybe one in Americas as well, although it's not talked about so much. These are summer, or Northern Hemisphere summer, June, July, August, September type monsoons, and maybe there's some Southern Hemisphere, definitely a South American monsoon, and maybe a South African monsoon as well. So, one question is, how are monsoons impacted by climate change? And although this is not particularly the best figure, what it shows is, well, actually one feature of climate change is that this is the temperature change. So the way we do this is to say, let's look at the temperature change relative to some historical period. So we don't look at the absolute temperature, we look at the temperature change. So this is the temperature change in the future. So it's going up here to about, well, actually this dark color is 20. Oh no, this is actually the temperature. I wonder why we haven't. 2.5, not 25. I was thinking it can't be 25 degrees warmer than. Thanks. This is better, is it? Okay, I'll try. Oh, you're right. This is better. Yeah, even without my glasses on. So one feature here of climate change is that the land areas warm more than the ocean. So if you talk about 1.5 degrees warming or 2 degrees warming, that actually means, maybe 2 or 2.5 degrees warming over land, and actually also more warming over the polar regions, which are a bit cut off here. And here's the change in the rainfall with lots of contours overlaid on colors, so it's not very useful, but I'll just cut to the chase, which is the bit of text and the animation. So in the model simulations, and because of reasons of what we understand in terms of the physics of monsoons, we expect them globally to increase in intensity in the future. In the past, there's been a bit of a trade-off between the aerosol impact on monsoons and the greenhouse gases. So remember, the aerosols causing cooling and the greenhouse gases causing warming. But that aerosol forcing is diminishing and the greenhouse gas forcing is getting stronger and stronger. So we expect the greenhouse gases to win out. Now this is, if you like, a sort of global picture of monsoon. As we've been discussing in our meeting in the last few days, there are local factors which might be important as well. So maybe the warming in the Indian Ocean also impacts the monsoon simulation. The Indian Ocean is warming quite rapidly in comparison to other tropical oceans. Maybe also land surface characteristics. So there's still some research to do here about quite the regional aspects of monsoons, but this is a kind of global constraint coming from the idea of just having global warming, and actually the idea that the land warms more than the ocean. Next, I'm going to talk about something called the El Niño Southern Oscillation, which is known, of course, to impact the South Asian monsoon. So I've got a little cartoon here that moves. This is a schematic of the Pacific Ocean. So India's over here, cut off. And the colors here are representing the temperature of the ocean, the sea surface temperature, SST. In the normal conditions in the Pacific Ocean, the water is warmest in the West Pacific, and in fact it's rather cool over in the East Pacific. Some people describe the East Pacific as a kind of oceanic desert. It's cold and it doesn't rain very much there under usual conditions. There's a sort of circulation cell which moves around, which means also that the rainfall in the Pacific is mainly concentrated over this area of warm sea surface temperatures, and the area is descending in the east here, so that's drying out the atmosphere and leading to reduced rainfall. You may get a bit of drizzle in the low-level clouds, but much reduced. And then there's the ITCZ, Intertropical Convergence Zone, which is sort of north of the equator. This feature in the ocean is the thermocline. So it's a region of sharp gradients between this warm water here and this cool water below. And you see, because of these winds blowing here, actually this cool water is being sort of sucked up to the surface. And so it's part of the reason why the East Pacific is quite cold. during an El Nino event, so something may trigger this warm water to move over into the central Pacific. Because the rainfall likes to rain where the warm water is, then that changes the convection cells, so the rainfall moves over into the central Pacific, and sometimes over here into the east, so the East Pacific desert can get rain. Then there's a series of feedbacks between the ocean and the atmosphere. This thermocline is flattened. The upwelling of cold water in the East Pacific is significantly reduced. So the whole thing feeds back. So you get this kind of period of, maybe half a year. And we had one of these events in 2023 where the sea surface temperature patterns in the Pacific are significantly changed. The rainfall is shifted around. And in fact, that influences the climate over many parts of the world, particularly around the Pacific Rim, but also possibly even into the Atlantic. So again, another question is what might happen to this under climate change? We've known actually for a while that one of the robust signals of the impact of climate change from the models is that this shifting of the rainfall pattern happens more frequently. The El Nino, as defined by the rainfall, which is important for the teleconnection, the connection patterns around the world, is moves more swiftly, more easily, if you like, into the Central and East Pacific, and happens more frequently. And then we looked at something called the time of emergence of this phenomena. So our question was, when might we be able to detect this El Nino has changed? So you can do this because we've got lots and lots of different model simulations. The models now can do a reasonable job of simulating El Nino events. So we've got two measures here of this so-called time of emergence of SST variability and rainfall variability. The dashed line here is where we say, we think we can detect a change at some point in the future. If we're looking at the SST variability, we don't detect a change till about 2070. But actually, if we look at the rainfall change, we think we will be able to detect a change in the El Nino Southern Oscillation in around 2040, which is only really 20 years' time. The gray shading is an uncertainty bound, so there's quite a big uncertainty around this. And the other interesting feature is that these different colored lines here are the different scenarios, so SSP 126 and SSP 585. And in fact, this time of emergence is happening pretty independently of the emission scenario, which was, I think, a bit of a surprise to us. So that this could mean that even if we do strong mitigation actions to limit climate change, we might still see this change in El Nino happening regardless. So the real lines are here, and of course there's no real ENSOs in the future. Well, there will be real ENSOs in the future, but there's no and the precipitation record is not long enough to actually put a curve on this line. So this is in model world. You're right, Raghu. So that's the caveat. Increasing frequency and severity in as little as 20 years. As I mentioned, El Ninos have these things called teleconnections, which means that they affect climate in other parts of the world. One of the famous teleconnections is the connection to the temperature in the Northwest Pacific. No, this is the Pacific North American pattern, so it's in northern Canada and Alaska, northern North America. one thing that we noticed in the climate models is that this teleconnection weakens under climate change. So, this is actually a useful signal for seasonal forecasting. So usually, if you have an El Nino event, you expect warmer than average conditions in this part of the US and, maybe in California down here. But we noticed this weakened in the CMIP models, and we did a few experiments to work out why this was the case, and it turns out to be because of this shift in the shift in the rainfall patterns further into the Central and East Pacific. So this, for those who know about it, the Rossby wave source has moved into the east and is weakening the teleconnection. So this is one of these things that we probably wouldn't have been able to guess beforehand about climate change without running these complex models and simulating all these different processes. Maybe less of interest to you guys, but more of interest to me is what's happening to the climate around the UK. What we did in this study was to look at a very high resolution climate model. So remember, I showed with the grid boxes covering the Earth. Generally, we like to try and make the grid boxes smaller and smaller, so it makes the numerical scheme more accurate. So that's what's been done in this particular case, changing the size of the grid boxes in both the atmosphere and the ocean. Well, I won't explain what this graph is, but what basically happens is that this is to do with the Gulf Stream, which is a feature in the Atlantic Ocean. The storms. The storm track actually passes over this part of the ocean. The storms generally pass over this warm bit of ocean here. They get energized, and if they get energized, then by the time they get over to the UK, they're actually a bit stronger. And this eddy-rich ocean actually, so the very high-resolution climate model actually predicts a splitting or a separation of the Gulf Stream further into the Atlantic, warm sea surface temperatures, and an increase in these storms. So this is a measure of storm activity under climate change in the high-resolution model and a lower resolution model. So this is an indication that, we don't know everything about climate change using the current generation of models. If we change something, then maybe we see a different result looking into the future. And, well, without showing any kind of scientific graphs, just this flashy animation, which, as I mentioned, someone made for me. Another feature or another study that was performed in this project was looking at changes in rainfall in the polar regions. So more and more, because of global warming, more of the precipitation landing in the Arctic and in the Antarctic is not falling as snow, but it's falling as rain. And that actually has a kind of destabilizing impact on the ice. So it means it can absorb more long-wave energy and possibly melt more. So there's a potential feedback here, if you like, between global warming and the ice in the Antarctic and the Arctic, which may even accelerate climate change. So, this is another, that sort of so-called thermodynamic change might have been something we would have expected from climate change, but then this is using the model to verify that with a more complex representation of different processes. Now I just want to spend a few minutes talking about some indices of extreme weather, mainly talking about extreme temperatures. So it stands to reason if you increase the average temperature of the Earth, then the hottest places will get hotter and will experience more extreme temperatures. So if you think about the temperature on the hottest day, if the distribution shifts, then that temperature of the hottest day also shifts. And But there can also be feedbacks and nonlinearities, which means it's not just a simple statistical shift of the distribution, but maybe some interesting physics going on. So this is an example. So in 2021, there was a record heat wave in the Pacific Northwest. It's a so-called heat dome. What we show here is the daily maximum temperature. So that's, if you like, the hottest day of the year. And it's a scatter plot against the global mean temperature. So it's just saying that there is a subtle shift. So there's a slight upward trend here. So as the global mean temperature warms up, then the temperature of the hottest day also warms up. And you can fit something called a generalized extreme value distribution to that curve, to that data, which looks a bit like this. And then you can say, well, okay, you can write something called the return period, which is how long you would, on average, wait between one extreme event and the next extreme event against the value of the extreme event. And you see here, if we took the data up to 2018, the fit, that you see the fit, and we see the extreme value, this is the 2018 heat wave, fits within the distribution here. So everything seems to be behaving nicely. This return period idea has some assumption about the stationarity of the climate. Obviously, we're not in a stationary climate because we have climate change. And then if we look at the 2021 record heat wave in the Pacific Northwest, the heat wave is off the scale. It doesn't fit the distribution anymore because of the impact of climate change. So this means that this record is very much higher than would have been expected from just some simple statistical idea of the hottest day of the year. And then you can do that in different parts of the world. So here, so this you see these kind of regions here are some classification of different regions of the Earth. They're actually classified according to, I think, the population size. So if it's smaller, then they're more densely populated. But what it's asking is, looking at the observations, where in the world has the most recent extreme event been outside the range of the distribution, like the Pacific Northwest event. So that is the Pacific Northwest event, so in the blue here. So there are a few regions in blue which have seen extreme temperature events which were entirely not expected, entirely unexpected in comparison to the historical record. There are other regions, and these are the pink regions, that have not seen those record events. So they might actually be in line for seeing one of these record events. And the reason why that is important is because often the way that climate adaptation works is that a country or a region adapts to the most recent extreme event that they experience. So you think, well, it can't be any worse than the last time we had a heat wave. But for these pink regions, it could be that there's a kind of a big heat wave stored up that will be outside the range of their current adaptation policy or their current infrastructure which deals with heat waves, like having cooling in hospitals and things like that. Some regions of the world you can't do the calculation because the GeV doesn't fit very well. So you can do this with models as well, but that's just one example of extreme events. Here's just another example of looking at the frequency of hot extremes under two different scenarios, so a 1.5 degrees Celsius world and a 2 degrees Celsius world. So it's the change in frequency of hot extremes. So where it's red, there is a bigger change in frequency of hot extremes than other regions. So that's generally in the tropics. Even hit with this green color, there's still some increase in the heat extremes, but not as big as in the tropics. This is just an indication of where, again, going back to this idea that the models are not perfect. So what instead of this is all the models, all the climate models that we have, this is where we just did some estimate of what we thought the best models were. And this is actually the difference plot between this one and this one. And in fact, the sort of take-home message is that the good models, the models which we think should be more reliable, have a bigger change in extreme than the situation with all the models. So this, bringing in some idea of the physics and bringing in some idea of the observations, we can filter out some of the models and then just look at a subset to see if that makes a difference to our result, which it did in this case.
So the confidence is still at multi-degree scale.
Sorry?
The confidence in these changes is still at multi-degree level, not even at the
Yeah.
resolving region.
Yeah. I mean, you see. I mean, okay. Take your glasses off. You'll see like a large-scale pattern. Obviously, there's some detail here, but again, we shouldn't really be looking, somehow at the detail of all these things. This grid box next to this grid box. We're still really in the process of looking at the kind of large-scale changes. And then one final thing, or not quite final thing, on. So this is instead of just looking at temperature, it's looking at something called the wet bulb temperature. So this is incorporating information about temperature and humidity. So you imagine that, if you're working outside in agriculture or something, and you're experiencing a very, a strong heat wave and also high humidity, this can be really bad for your health. And again, it's this idea of a return period for the wet bulb temperature greater than 31 degrees. There are lots of different measures of this heat humidity. None of them perfect. So 31 degrees is considered dangerous, and above 35 degrees is considered deadly. But this is the return period for the 31 degrees C, I think. And it's, you can see in the present day, or the reference period, there's not a great deal of occurrence of these high heat and humidity events. But as the global mean temperature goes up, you get more and more regions of the planet where you see this. And then some regions, where the yellow colors indicating this basically happening every year. So this, this is a real problem. Particularly if you're working outside. And then you can actually also convolve that measure of the hazard, so the heat humidity extreme, with the population, so how many people would be exposed. So it's more kind of like becoming a measure of risk. And you can't see all the details of that, but this is the number of people days, and that's, 1 million. So where it's the yellow color, it's like 1 million people would be exposed to this high humidity temperature event, given some assumptions about population growth, and I guess also some assumptions about the number of people working in jobs which would require them to be outside. So this is where it becomes quite challenging, bringing in aspects of human behavior into the whole picture of climate change. My work largely focuses on the physical aspects and the hazards, but I know some people working on this idea of exposure, of vulnerability, etc. And this, I think, is really important that we do that, but it certainly is a tricky problem. Okay, so just this is a kind of summary slide. So As I mentioned, this is not a comprehensive talk about regional climate change, but it gives some examples. And we went from the pole to the equator, so remember the polar rain, the precipitation in the polar regions falling more as rain rather than snow, the intensification of the monsoons globally, severe storms in the Atlantic becoming more frequent, severe El Nino events also becoming more frequent, severe meaning when the rainfall moves into the east, the central and east Pacific, and these hot, humid extremes becoming more frequent into the future. So, I think that's it. Thank you very much.
Thanks, Matt, for the nice presentation giving an overview of impacts of climate modeling and impacts of climate change. Now, the floor is open for questions.
So, thank you, Professor. Fascinating lecture, thought-provoking. My question is, like we study geostatistics, and this kind of thing are failed in feedback and normality condition. That's where the physical models comes into action. So, what do you think? What kind of statistics we should study to better understand, model this kind of things? Especially, you are talking about that qualitative aspect, human behavior and this kind of thing. What kind of model do you suggest as a statistics we should study?
Yeah, so I won't declare myself to be an expert on statistics, far from it. But I think we need, I often describe what I do as a kind of a bit of a mixture between statistics and physics and mathematics. So we kind of need a mixture of all these things. So I think, and in particular, the other thing that, of course, on everyone's lips is the idea of machine learning. And can we use that machine learning approach to better quantify the link between, as you put, the hazard and the people. So I don't think there's an answer to your question in terms of you must use this type of statistics, but I think we should use them. And if you're studying them, then I think you can come up with some good ideas about what to do.
Yeah, so.
Hello?
Somebody is saying something? Yeah, is somebody talking? Can you use your El Nino figure to say quickly the problems model have in the East Pacific trend?
Yeah.
And what that could, does your emergence framework work despite that bias?
So we looked at both the mean, maybe I don't need to show the figure, but we looked at both the mean change in sea surface temperature and the variability. And when you look at the mean change, none of the observed records show an emergence of the SST change in the East Pacific. It's a weird thing, this time of emergence, because it's a signal-to-noise ratio. So you've got a signal divided by noise. In the Eastern Tropical Pacific, you have a huge noise term because there's ENSO going on. So in fact, you have to have a pretty strong signal in order to see the signal emerging from the noise. If you take a big box around the Pacific, you can see that it does. But in the eastern part, it doesn't, because the observations are not behaving like the models, or the models are not behaving like the observations. So I think that's still an open question, this pattern, this change in SST patterns in the Pacific Ocean.
Considering the impact of El Nino, you think that's the results are still not?
Well, okay, so what, the recent paper that Masahiro Watanabe led and Sarah Kang, we looked at all the physical processes responsible for either East Pacific cooling or East Pacific warming, and we concluded that all of the physical processes that could be responsible for the Eastern Pacific cooling are transient and will not be sustained into the future, like Southern Ocean cooling or the thermostat effect, or various other things. So the conclusion of that paper was the model patterns probably win out because that's the long-term held and, sorry, this is getting a bit technical, reduction in the, well, I can never repeat the argument because I don't really understand it. But anyway, the basic reduction in evaporation because of the reduction in the trade winds.
Thanks, Matt, for this nice talk. It gives a huge, very good overview of the entirety of climate change science. I have two things to actually ask you. The first thing would be the air quality that you have been talking about, the air, because of air quality and its impact on health. We are imposing, a lot of policy decisions, and maybe they are coming up and we are cleaning the air, right? And that's why you said one of your initial slides that the greenhouse gas warming could be actually overtaking it. So, so what do you think? I mean, how do you? What is your opinion on this? That how one should be then looking into the air quality or cleaning the atmosphere through aerosols because of aerosols? The other point I wanted to ask you is on this, the concept of solar geoengineering, the solar radiation methods.
Yeah.
So what is your opinion on that? I mean, so I think because they come with lot of, side effects.
Yeah.
I wanted to know about that.
Yeah. So, well, first to say about the aerosol, I think the thing I would say is that we still have a lot to understand about how the aerosol signal impacts on the large-scale climate dynamics, and probably we still have a lot to do to represent the aerosols correctly in models because it's quite a complex process. The aerosols are emitted and then they're transported around, but actually they are, if it rains, then they're washed out of the atmosphere. So their lifetime is actually pretty short, even though if you look at the forcing patterns, they tend to be quite sort of global in nature. So I think there's still lots of work to do on that. On the solar geoengineering or climate intervention, yes, probably we can do the research with our models to work out what the impacts of that solar geoengineering would be. Whether we ever get to do it is a political question. Yeah. Do we trust the politicians? So I probably leave that open and maybe a discussion over a drink.
Thanks, Matt, for the wonderful talk. There's a hypothesis floating around that as the ocean temperatures increase, there is increase in algal blooms, and then they sequester carbon and mitigate climate change. Is there any real evidence for that?
So I don't think that process would necessarily be represented in the models or represented very well. So I don't really know about that.
Thank you.
I'd be interested to learn more. You have some papers? Okay.
Thanks for the nice talk. My question is about Indian monsoons. In general, monsoons will intensify. But if you look at CMIP 5, CMIP 6 models, especially, and ask this question about Indian monsoon, the answer is 50-50. Some models say intensify.
Yeah.
So there, I mean, going back to what Raghu also pointed out, that how many grid points do we need in a climate model? How big of a region do we need so that we could, first of all, trust models? And second, if we want to pick good models out of all models, how much can we rely on them, considering that the good models are picked based on their ability to capture global patterns rather than regional ones?
Yeah, you can always pick. You can always develop your metric of model skill based on some local processes. I think that's allowed. I'm not sure it's really a question of resolution in terms of representing the Indian monsoon. I suspect that the feedbacks between the land surface and the atmosphere might be equally important. So my colleague Andy Turner, so the Metofis model is pretty notorious for not having much rainfall in the interior of the subcontinent. It all falls out over the Ghats, and then maybe sort of comes back again when you get into the north, but nothing much in the interior of the. So what he did was to change the land surface so it was an ocean rather than a land, and that improved the monsoon simulation considerably. So there's obviously some feedback there. You know, if you have an infinite source of moisture, you get a pretty good looking monsoon. So there's probably some recycling of moisture in the, you know. So I think there are all these things are still, you know, hot topics in climate research.
I have a short question, second question. Which, my second question is about the WBT plots that you showed, wet bulb temperature.
Yeah.
I was just looking at some of the recent data about mortality related to heat waves. And it seems that's quite a lot in Europe and not as much in India as compared to the delta T we see.
Okay.
And I was just thinking, what's your take on that? I have not read literature myself much, but
yeah, I
if you
don't know much about human physiology to be able to. Maybe you're well adapted to humid events, and us white, pasty Northern Europeans are hopeless.
Because I saw the difference is 2 orders of magnitude, and I thought even if there's some error in reporting, it's difficult to reconcile.
Yeah.
Thanks.
I guess it's a serious issue actually, so shouldn't be joking. But, yeah.
Thanks, Matt. I thoroughly enjoyed listening to you. I have a question regarding the return level plots that you showed.
Yeah.
So the top one, so the 2021 event was excluded from the series and then you calculate?
That's right, yes.
So let's say now a more or a similar nature event, let's say, shows up in 2026.
Yeah.
Then even though that event's magnitude would be in an absolute sense quite extreme, but because you have included the 2021 event, that future events return period is going to come down.
Yeah, so in fact, I think what happens is the GEV fit fails when you include this point, because it just says, the fit program says, that can't possibly be the extreme value. It's too big. So you can imagine trying to move this curve up so it like, but also be consistent with this data. So I think we had to do it that way, otherwise we couldn't have done the GEV fit. Yeah.
A corollary question related to that. You did mention briefly that you could do it with the physically based models also.
Yeah.
Is there a physical upper limit, like in hydrology we have the probable maximum precipitation. Is there a physical upper limit on the maximum daily either Tmaxes or the WBGTs that one can see for a region?
There may be an effective upper limit because you would have to. You can imagine a scenario. What often happens is in mid latitudes, if you have soil moisture and it all dries out, or at least it dries out in the top, a few centimeters or whatever, then all the solar radiation which is coming in is heating the surface rather than evaporating water. And if you imagine you had a heat wave that lasted 2 weeks, you could probably calculate an upper limit on, given a clear sky solar and a layer of soil of a few centimeters or tens of centimeters. I don't know if anyone has done that. So I think it might be possible to calculate that, but I'm not sure we know what it is.
Thank you.
Hi, so you mentioned that ENSO's teleconnection with climate in northern North America are weakening, but what about its teleconnections with Indian monsoon? Because ENSO is like becoming more intense and more frequent, but what about its connections with Indian monsoon?
We just got a student started on that, so we haven't done the calculations yet. We did do the calculation between the ENSO teleconnection, for the ENSO teleconnection to Northern Europe, which is quite weak, but that actually strengthens under climate change. So we might get a bit more predictable signal for seasonal forecast. But we haven't done the Indian monsoon connection yet. So I'll come back, or the student can come. He can tell you about it.
Why did the eddying ocean lead to more extreme events?
Oh, because of this representation of the Gulf Stream. Under climate change, there's the high so it's the ocean resolution which is important. in separating this Gulf Stream and changing the sea surface temperature patterns in the region where the storms get a boost as they come. It's basically the cold air flowing off the Rockies goes over the warm SST, and there's a boost in the energetics. So I think, yeah, it's the ocean resolution and that separation of the Gulf Stream.
But it's region specific.
Yeah. It's almost, if you like, chance that the storms is it chance that the storms happen in the region of the Gulf Stream? Not sure. Yeah. Yeah, it is. Yeah. But it's like a high-res MIP, so it's like 1950 to 2050 or something like that.
Yeah, thank you, Matt, for your great presentation. So I just had a small question to ask you. So with a lot of models coming in the market now, and with AI in the picture, and a lot of AI models also coming recently, like GenCast, GraphCast, Pangu Weather.
Yeah.
And in the case of temperature, the Indian models and the global models are also, they are also giving really good forecast, at least in short-term weather prediction. So I just wanted to ask you, like maybe 5 to 10 years down the line, what's the future of climate research, and what would be the areas in which we'll be looking into for
I don't think we
research?
probably have to wait 5 years or 10 years, but I'm sure we'll see one. I'm sure we'll see an AI climate model coming soon. I'm sure many people are working on this. It has there are lots of issues, of course, like you really want to make sure that you're conserving energy, because when you start doing so if you take the machine learning weather forecast models and run them for a long period of time, they drift considerably, or many of them do. So they're obviously not conserving energy or conserving water or momentum or all these kind of things. So there's some work to do there, but I'm sure there are bright people around in the world who will do that.
Okay. Yeah, thank you so much.
Thanks, Matt, for a wonderful talk. In fact, one of the things I'd like to highlight that one of your slides says that climate change persists even after net zero.
Yeah.
And that's a very important message for the institute, for everyone, because when we interact with people, people think that, yeah, just achieve net zero, climate change is gone. There is a magic wand which will stop climate change, so you don't have to worry about climate adaptation. You don't have to worry about climate science. Just do CCUS, just do green hydrogen, you are done. So it's a very important message for everyone. Even not only outside IIT Bombay, even for inside IIT Bombay, across the departments. People should understand, those specifically who are working in sustainability, green energy, and so on, they should understand that climate adaptation is equally important for India. So thank you.
But don't stop working on those things, because they're really important.
Yeah, don't stop, but they are equally important. So that's very important. So thanks for a wonderful talk.
Thank you very much.
And on behalf of Institute, this is on behalf of Institute, a small
Thank you very much.
appreciation.
We need a photo. I'll take my glasses off.
And this is on behalf of
Oh, blimey.
studies. Yeah.
Okay. Thank you so much.
Thank you, everyone.